First speaker today is Andy Skemer. Andy is an assistant professor here at UC Santa Cruz.
Thank you. So I'm going to start with, I'm going to start with what I think was the same figure that Jacob was showing from an unknown Adam Burrows paper. And the general idea here is that you're looking at these blue curves are stars, these green curves are brown dwarfs, and these red curves are extrasolar planets, meaning that they're below the deuterium burning limit. That's how the dividing line is shown. And you've got age on the x-axis and temperature on the y-axis. And so what you can see is you've got spectral types here. These are M dwarfs, L dwarfs, and T dwarfs. Within these categories, the planets and the stars and the brown dwarfs all look pretty much the same. So for something that's, say, 2400 Kelvin, depending on your age, you could be a star, you could be a brown dwarf, or you could be a planet. I went in the wrong direction. Star, brown dwarf, or a planet. And generally speaking, you're going to look about the same. And the mass doesn't make too much of a difference to the spectrum. So what does make a difference to what the planet looks like, to everything about its environment and as an extrasolar world, what does make a difference is temperature. And so rather than sort of looking for things at lower and lower masses, I'm interested in studying things at lower and lower temperatures. And so this talk is going to be about some of the tools we use and directions that we're going in learning about the coldest atmospheres of extrasolar planets. So I want to start just by explaining that it's actually easier to find these cooler planets by working at the longer wavelengths. And so that's going to be a theme of this talk, is that if you want to study colder exoplanets, you have to work at longer wavelengths. And it's just as obvious as saying that colder black bodies peak at longer wavelengths. Of course, these things aren't black bodies, but to first order, you can sort of assume they are, and their molecular features peak at longer wavelengths as well. So here I'm showing wavelength versus contrast on the y-axis. So contrast is how much fainter than the star you have to be able to detect this thing. So if you can get to a 10 to the 4th contrast, 10 to the 4 times fainter than the star, you can detect things at these wavelengths. So at the top, we've got some of the directly imaged planets that we've found so far. And these are really the freaks. We've looked a lot for directly imaged planets. There are many stars where we have the sensitivity to detect 1600 Kelvin planets. We're not finding a lot of them. And for things of these temperatures, you can see that the longer wavelengths are a little bit easier. There's less contrast that you need to be able to detect this planet at 4 microns than at 1 micron. And as you get colder and colder, that becomes more extreme. So by the time you get down to something like Jupiter, all of the flux is basically coming out at 5 microns. And even for things that we think are just probably more common, we don't know of a whole lot yet. We haven't had the technology to necessarily detect these things. We've never detected a 400 Kelvin directly imaged planet, but for example, if you just look at an average age star in the solar neighborhood and talk about the maximum temperature you could be if you had a really massive planet, it'll be about 400 Kelvin. And in order to be able to define those things and to study just even the most basic properties like the exoplanet's luminosity, you need to be looking at these longer wavelengths. So just to drive this point home, Beta Pictoris b is the hottest directly imaged planet right now. It's 1600 Kelvin, so that would be the example where working at the longer wavelengths gives you the least benefit. But here are 2 images taken simultaneously, so 2 cameras on the same telescope, same AO system, looking at the same star, and you can see that the planet is much, much brighter at 5 microns than at 1 micron. So it was much easier to detect here. And you can ignore these little side lobes. That's part of the data reduction process. But much, much easier to see at 5 microns than at 1 microns. And that becomes even more extreme as you work to colder and colder objects. So for exoplanet imaging, you take an image, you measure how bright it is at a whole bunch of different wavelengths, and then you compare those to atmospheric models. And so we started doing this in the thermal infrared with the HR8799 planet system. This is something that Jacob showed this morning. So 4 directly imaged planets around the same star. And by looking at the longer wavelengths, you learn a lot of different things than people had been doing at the shorter wavelengths. You want as broad of a wavelength as possible when you're characterizing exoplanets. So here's an image that we took in 2012, and around the same time, Mark Marley, who's in the back of the audience, had some atmosphere models that he was using to try to explain mostly the near-infrared photometry points. So the black points are data, and the red points are model photometry. But you can see that in the thermal infrared, these models were off by quite a bit. And these models were motivated by brown dwarfs, things that we have studied in more detail. But when we started to look at extrasolar planets, some things did look a little bit different. And so this, besides being an easier wavelength to detect planets and a wavelength where you can learn the most about their luminosity, there seem to be some real discrepancies here that we can study and learn about these atmospheres. So Mark and I teamed up and we went and got a whole bunch of narrowband filters throughout this wavelength. So we wanted to figure out what was going on from 3 to 4 microns. We put a bunch of filters inside the same instrument that we had used to make the last image and sort of worked our way through them. So spent 20 minutes per filter instead of doing them all at once. And that's a slow way of taking data. It's not particularly efficient, but we were able to get photometry at 6 different wavelengths and begin to measure the properties of these extrasolar planets. And with that, and comparing it to models, we were able to show that some amount of patchy clouds was necessary to explain all of these photometry points. Non-equilibrium chemistry, where hotter material from deep in is being mixed into the upper parts of the atmosphere and it has different molecular characteristics. So we're just sort of barely starting to work on this stuff right now. With directly imaged planets, every photometry point you get is special. Every time we've ever looked at a new planet in a new wavelength, there's been a whole paper just because it's allowed us to refine these models and learn how they were different than some of the previous cases that we had been looking at. So from 1 filter to 6 filters, we learned a lot about extrasolar planets. And the next step is that we would like to go to even more filters. And the way that you would normally do that is with spectroscopy. But spectroscopy, Jacob did have a slide on this showing an attempt to take a spectrum of an exoplanet. And it's really quite difficult to do it with a slit. Just if you try to put a slit on one of these directly imaged planets, it's really hard to keep it in there and it's really hard to distinguish the light from the star. So people use what are known as integral field spectrographs. And what integral field spectrographs do is for every pixel in the image, they make a little spectrum. And so here's an example for one. Basically, this is the world's first 3 to 5 micron integral field spectrograph. And we built it specifically to study extrasolar planets. Most integral field spectrographs work from 1 to 2 microns because that's where the extragalactic observers like them to be. But for exoplanets, like I said, we'd really like to be working at these longer wavelengths. And so this is a picture of Io, which is one of the moons of Jupiter, and then that's a volcano on it, Loki Patera. And so for every pixel in this image, we've dispersed it into a little spectrum. You have a little lenslet array that focuses the light of each pixel, and then you get a prism and you put it at just the right angle so that these spectra don't overlap and you can extract them. So a zoom in onto this volcano, you can see the shorter wavelengths, 2.8 microns down here. The longer wavelengths, 4.2 microns, are up here. And now we have basically an image of this object at every single wavelength. So if you just sort of for some intuition on this, if you're looking off of the volcano, the objects are a little bit brighter at this edge. There's some telluric effects right here where it gets brightest right here, but sort of brighter at this edge. And when you look at the volcano, they get brighter on the longer edge. And that's because you're seeing reflected sunlight at the short wavelengths, but when you get onto the volcano, you're seeing thermal emission as well. So if you take the bottom pixel in each of these and add them up and make an image, and then work your way up the spectrum, the bottom pixel of the spectrum, the second to bottom pixel of the spectrum, the third to bottom pixel of the spectrum, and you make a whole lot of images out of it, here's what that same image looks like extracted. So now we have Io at 15 different wavelengths, and here you're seeing the reflected sunlight going from 2.8 microns to 4.2 microns, and the volcano turns on. So that's how integral field spectroscopy works, and you can do the same thing with your star and your planet, and you can use all of those complicated data reduction techniques that we were learning about this morning. And because it's taking an image, you can use those techniques, and because you're also getting images at all these different wavelengths, you get a spectrum of the object as well. So this instrument's brand new. We had first light last year at the Large Binocular Telescope. Soon after first light, the adaptive optics system at the LBT failed, so it's been a while. We've just recently been getting back on sky, and so those HR 8799 planets I was showing you before, we were taking spectroscopy of them just last night. And so that will allow us to, there's already spectra at sort of the shorter wavelengths, but now we'll have them at the longer wavelengths as well. Okay. Moving on to a slightly different topic, the coldest directly imaged planets are about 500 Kelvin. So if you want to go colder than that, one way to do that right now is to look at isolated brown dwarfs, free-floating brown dwarfs. And so the coldest brown dwarf that we know of is 250 Kelvin. We can't study a real bona fide extrasolar planet at 250 Kelvin. If we want to understand exoplanet atmospheres at those wavelengths, we can look at an isolated brown dwarf. So this guy is 5 Jupiter masses. It's 2 parsecs from the sun. It's the coldest object outside of our solar system, compact object at least. It's not like the microwave background is colder, of course. And it's the first object likely to have water clouds in its visible atmosphere. It was discovered by the WISE spacecraft because it's moving extremely quickly on the sky, and then you take a parallax measurement and say, hey, this thing's really faint, and it's only 2 parsecs away. So it has a J-M color, 1 to 5 microns for the non-astronomers in the room. It's 11 magnitudes, or a lot of times brighter at M band. So 5 microns is a difficult wavelength to observe from the ground, but it was the only way to get a spectrum of this. Nobody else has been able to take a spectrum, and not for lack of trying. So the black points here are data points, and then the blue is a model. Since Mike Liu's in the audience, I'll tell him 0's at the bottom since he doesn't know it. And so this is the spectrum right here, and the blue curve are models by Caroline Morley. And basically, considering that we've never observed an object colder than 700 Kelvin at these wavelengths, this is a pretty good match for a first try. We get basically all of the wiggles in the right position. And all of these wiggles, according to her model, are due to water vapor. And then we went through and just did all of the most basic things that you do the first time you can take a spectrum of an object this cold. This is the first time we've ever had an object cold enough to have water clouds, the first time we've ever had an object that kind of looks, in the same temperature range as Jupiter. So a lot of what we were doing was copying what the Jupiter people had been doing 40 years ago. I was like reading all these old papers about Jupiter, and they had done some very complicated physics and chemistry, and it was easy to just sort of cherry pick the easiest things that they had been discovering about this. So the first thing we did was try to figure out if there are water clouds on it. And so we have our blue model which I showed on the previous plot, is the cloudy model, and then the orange one is the cloud-free model. And basically what the clouds do are they collapse the absorption features. They make them a little bit more shallow. And I wouldn't say that this blue one is a perfect fit or anything, but certainly adding clouds has improved our fit to the model. These are 1D models. This is the first time they've gone down to the temperatures where they need water clouds. So this was already a pretty good result that we can get it close to the range. So I wouldn't say that our cloud model is correct, but I would say that there's pretty good evidence that this thing has clouds. The next obvious thing is just to compare it to Jupiter. So here's a 5 micron spectrum of Jupiter in blue. And at the longer wavelengths, I would say that most of these features are kind of in the same area. Not this one right here, that misses. But the other ones, they're kind of in the right area, and maybe there's a little bit of a slope offset because of the difference in temperature between WISE 0855 and Jupiter. So at the longer wavelengths, water looks pretty good. The Jupiter atmosphere looks pretty similar. At the shorter wavelengths, Jupiter has phosphine absorption, which is evidence for non-equilibrium chemistry. 40 years ago, that was used to show that Jupiter is convecting from its hotter interior. But for whatever reason, WISE 0855 does not. So WISE 0855 is a little bit hotter than Jupiter. We seem to be getting less mixing, though, and that's something that we're going to be thinking more about. The last thing that we checked was for deuterium. So you can actually, in Jupiter, you can measure Jupiter's deuterium abundance right at this wavelength right here. And I wouldn't say that we've measured this terribly accurately. You can see here's a model with normal deuterium, or with no deuterium, then the blue is a model with Jupiter's deuterium, and the green is a model with 10x Jupiter's deuterium. But we can kind of distinguish these things apart. Probably not enough to do precision cosmology. But there is a hope that, as you build space-based telescopes, if you use a bigger telescope like the TMT and can get a higher signal noise detection, you might be able to measure how much deuterium is in an object. And that would also be one way of measuring the mass of an object. If you can look at multiple planets in the same system, you might be able to tell something about how these things formed. Comparative deuterium abundances is a really popular thing to do in our own solar system. So lastly, I just wanted to mention some future observations that might help us on colder exoplanets. On the left, I've got JWST, and JWST can take exquisite data of the isolated object, something like 250 Kelvin. That was a 30-hour spectrum with Gemini. Probably take 10 seconds with JWST at much higher signal noise and working, at wavelengths that we can't even do it. So it'll be tremendous for that sort of science. Cold exoplanets at very wide separations, several arc seconds, hundreds of AU from their host stars. JWST will be able to do that as well. What it won't be able to do is look at cold planets that are actually close to the star, things that we might actually consider to be more like our own solar system, more planetary formation type of things. And so the large ground-based telescopes are still going to be the best way that we can study those. We'll only get adequate data, kind of like I showed on those previous spectra. Those are kind of ratty spectra. That's about as well as we can do with ground-based data on the coldest things, but the slightly warmer planets we can do, and the real bound exoplanets we can do from the ground. So, thank you. So that's looking, if you look at Jupiter, you're looking through these cloud holes pretty much. And so that is a window between methane and H2 absorption that allows you to see deep into the atmosphere. We have temperature pressure profiles where we sort of guess where they come from, and I think the answer is 0.2 bar or 1 bar.
The question is more like, how is the effective temperature?
Is that right? The effective temperature is not actually determined from a model fit. It's because basically if all of the flux is coming out at 5 microns, and there's photometry at 5 microns that tells us the luminosity of the thing. The evolutionary models predict that everything is about 1 Jupiter in size for a reasonable range of ages. So you can calculate the effective temperature directly from that. It's extremely well constrained just from 1 photometry point. And then we can just use that for our model spectrum. I think your retrieval will be ratty, Mike.